Greetings, everyone. Learning as a hobby here. I wanted to continue today with the Appendix 1 for Spivak's calculus book. So I'm actually going to do the summary for the section for the appendix and the exercises all in one video, just because you'll see. Actually, I give very brief treatment to the summary for the chapter for the section because we've actually already done similar things like this in other books, like what's his name, Schifrin in Schifrin's book, and um, Exler and so on. So anyway, I'll go through it really quickly, and then we'll go through the problems. So let me bring up the summary for the section. All right, so I went over the chapter itself and the exercises for chapter 4 in the last couple videos. So here we'll do the appendix 1. Remember, there's actually 3 appendices to chapter 4. So here, basically what he does is he just talks about thinking about vectors in R2 as, in terms of two tuples. Sorry, thinking of points in R2 as vectors, and you can represent them as two tuples or similar, just a different way of thinking about points in the plane. But then you could add some extra structure to, the vector concept, because, for example, we could add vectors together. This is the formula that we use for that, and just showing geometrically what the interpretation of vector addition is. Maybe I'll explain this diagram here. So here, this is the vector w, and this is the vector v. And if we look at their sum, v plus w, by the definition, the v plus w has coordinates v1 plus w1, and the second coordinate is v2 plus w2. If you look at the picture here, the sum lies along the green line and the blue line. So if you look at the slope of the green line, which I'm calling L, just using the slope formula, you get v2 plus v2 plus w2 minus v2, which gives you w2 in the numerator, and v1 plus w1 minus v1, which gives you w1 in the denominator, which is exactly the slope of the vector w. So in other words, the green line L is parallel to w, and you could do a similar thing for the blue line. Just look at the slope and you'll see that it's parallel to the vector v. All right, so it gives you this geometric way to visualize the sum of or a geometric interpretation of the sum of two vectors. It gives you the diagonal of the parallelogram spanned by the two vectors. And using that geometric conception, it should be intuitively clear that addition of vectors then would be commutative, right? Because if you go along v, then along the green line to get to v, the sum, you get to the same point as going along w and then going along the blue line until you hit the sum. So, but you could also prove that using real numbers. Like I said, I didn't actually go through that here because we've already done this like a bunch of times, and I don't want to waste time going through stuff over and over and over again. So yeah, so these are some properties that he ends the appendix with. He talks a lot about it, so you should actually read through the appendix if you've never seen vectors before, because there's a lot of information that I'm leaving out here. But he goes over some of the important properties, like the commutative law for adding vectors, associative law, the fact that 0, 0 is the additive identity, and so on and so on, all these other properties here. So he does talk about scalar multiplication as well. If you multiply a vector by the scalar 1, you get the same vector back. If you multiply a vector by 0, you get the 0 vector, or in other words, the point 0, 0, and so on like that. So that's really all I'm going to say about what he talks about in the appendix. Like I said, I'm giving this sort of short shrift just because we've gone over this type of stuff a bunch of times already. But again, if it's the first time you're seeing this, you might actually want to read the appendix in detail. So I'm just going to jump right into the exercise set then for appendix 1, which I have here. There was actually only 7 problems to the section, but they all have like multiple parts. So but I did all of them, so we'll go through them here one at a time. Question 1 says, given a point v in the plane, let r sub theta v be the result of rotating v around the origin through an angle of theta. And he says, see the figure. I think, where did I draw the picture? So here, this is the picture here. So if you rotate, oh, actually, no, did I not? This was the picture I drew for the proof of part A. Did I not draw the picture? Oh, I see. The video box is covering it. That's why. In the corner, right in the corner here, I have the picture here. So if you have vector v over here, if you rotate through the angle theta here, I'm assuming that it's rotating counterclockwise, you get to the vector r theta v. So it's just a rotation, a rigid rotation. All right, given a point, that's what we're defining that notation to mean. The aim of this problem is to obtain a formula for r theta with minimal calculation. So let's go through it. There's a bunch of parts here. Let's go through them one at a time. So part A says show that when you rotate the point 10 through an angle theta, the coordinates are cosine theta, sine theta, and if you rotate the point 0, 1 through an angle theta, you get the coordinates negative sine theta, cosine theta. Let's look at the proof for that first, and then we'll look at the other parts. All right, so here's my proof for part A. The proof that rotating 1, 0 through an angle theta gives you the coordinates cosine theta, sine theta is essentially just you just use the definition for the trig functions, right? The point here has to lie on the unit circle, and if you remember the way that we define the trig functions, cosine is the x coordinate of the point on the unit circle, you know, where the angle with the horizontal axis is theta, and sine is the y coordinate. So you just use the definition of the trig functions for that. And then once you have that, we can find the coordinates for r theta 0, 1 by using the sum formulas for cosine and for sine. So to rotate 0, 1 through an angle of theta, that you take cosine of pi over 2 plus theta and sine of pi over 2 plus theta, and that gives you the point. Using the sum formulas for those two trig functions, which is what I did here, and then simplifying gives you what you want. So that's the coordinates for those 2 points when you rotate. Okay, part B says explain why we have, so essentially he's asking us to show that this rotation operator is linear. So it takes sums to sums, and it takes scalar multiples to scalar multiples. So here I'm just proving this, just talking about the geometry of a rigid rotation. So rigid rotations preserve lengths and angles, right? If you rotate a line segment through an angle theta, the length doesn't change. And if you have two line how do I do this with my fingers? You know what I mean. If you have two line segments that meet at an angle theta, and you rotated them through an angle alpha, the relationship stays the same, right? So if you look at the rotation of the vector AV, it's the point at a distance, absolute value A times the length of V. And that's because, if you have vector V and you rotate it through an angle theta, again, like we just said, it doesn't change the length of the angle, doesn't change the length of the vector, right? And all that A times V does is it scales the vector by some length. Since lengths don't change, the rotation has the length absolute value A times the length of V, and the angle that the angle that the new vector has is alpha plus theta, right? If theta is the angle between V and the horizontal axis. All right, so that shows that that's true. Similarly, all lengths and angles between r theta V and r theta W, like I said a second ago, are the same as that for V and W, right? The relative angles between the vectors are not changed by a rigid rotation, and neither are the lengths. So that it should be clear then that when you take the rotation of the sum of the two vectors, then that's the same as the sum of the rotated vectors. All right, so that's part B. Part C, show that for any point xy, we have this formula here to get the transformed coordinates. All right, so going down, we're just going to use linearity to do this. So r theta xy is the same as the vector r theta of x times 1, 0 plus y times 0, 1. Use the linearity properties that we looked at in part B, and use the the definitions that we looked at in part A, and that gives you exactly what you want when you simplify everything, right? So these are the formulas. And then lastly, in part D, they say use that formula to give another solution to the problem 423. That was the last problem that we did in the chapter 4 problems. So here it's relatively easy because you just plug in, wait, where did I write it? Over here. So the rotation there so in problem 423, you're thinking of it as a passive transformation. So the axes are rotating. Here we're thinking of it as rotating the vector itself through an angle of -π/4. So this would be like an active transformation, whereas the other one, I guess you could think of as like a passive transformation. So r -π/4, just plug in the value into the formula that we derived in part C, and you get the same answer that we got for problem 423. All right, that's essentially it. Question 2, given V and W, we define the number V dot W equals V1 W1 plus V2 W2. This is often called the dot product or scalar product of V and W. We've already talked about this in Schifrin. There's a bunch of parts here. Part A says, given V, find a vector W such that V dot W equals 0 and describe the set of all such vectors. So let's do that first. If you notice, there's a bunch of parts to this one. Okay, so if V has coordinates V1, V2, if you choose W to have coordinates -V2, V1, when you take the dot product, notice you get 0. And the set of all such points will lie on the line perpendicular to the vector V. You could see that from the slopes of the two vectors. The slope of vector W is, and the slope of vector V, if you take their product, gives you a value of -1, so they're perpendicular. All right, that's part A. Part B, show that V dot W equals W dot V, so commutativity. He also wants us to show that there's a distributive law and an associative law for scalar multiplication as well. Right, so here I'm just using the coordinates to do that, really very straightforward. So use the commutativity property of real numbers to do that. Use the associative property of real number, sorry, not associative, use the distributive property of real numbers to show the distributive law. And then same thing for scalar multiplication, just use the coordinates and use the associative law of real numbers and so on, right? I only showed one part here, but I just said etc. because it's similar. You just switch the A over to the other vector. Okay, so that's part B. Part C, show that V dot V is greater than or equal 0, and that V dot V equals 0 only when V equals 0. Hence, we can define the norm, which is written that way, as the square root of V dot V, which will be 0 only for V equals 0. And then he wants us to say what the geometric interpretation of the norm is, right? So part C. So just using the definition of, let me just readjust here. Using the definition of the dot product, V dot V is V1 squared plus V2 squared. Obviously, that's a sum of squares of real numbers, so that's always non-negative. And the sum of squares can only be 0 if the two numbers are 0. So that means that V would have to be 0 if the dot product was 0. If you're taking the dot product of a vector with itself, if that was 0, right? The norm is the length of the vector V, which you can see from the Pythagorean theorem. Okay, and then part D, prove that the length of V plus W is less than or equal to length of V plus length of W, and that equality holds if and only if V is 0, or W is 0, or W is A dot V, A times V, that's scalar multiplication there, for some number A greater than 0. So essentially you're saying prove the triangle inequality for vectors. So scrolling down here, all I did was I used the formulas that we derived in problem 49A. Remember, we derived, if you watch that video, we derived a couple of inequalities. So I just used the first inequality in that problem. You just plug in the coordinates and you get what you want. Okay, and then for the other part, if you assume that W is a scalar multiple of V, then if you notice, you get equality. And then, so here that would take care of the case where W is 0, which basically takes care of all the cases because of symmetry here. But, just to be completely, I don't know, do all the cases out. If V is 0, then obviously you get equality as well, right? So which I did down here. Okay. What was that? What letter was that? Letter D. Last one, letter E. Show that V dot W can be written in that form. Okay, so here I'm just using the definition and some of the properties that we derived for the dot product. So V plus W, the norm of V plus W squared minus the norm of V minus W squared over 4 is given by this expression, just by the definition of the norm here. So V plus W dot with V plus W minus V minus W dot with V minus W all over 4. When you multiply everything out using the the distributive law and everything, notice that a bunch of things cancels. V dot V cancels with negative V dot D. Same thing with W dot W and negative W dot W. And 2V dot W plus 2V dot W is 4V dot W. And then you're dividing by 4, so that cancels, and that gives you the dot product V dot W, and that's the proof of the formula. Right? Question number 3. Part A says, let R theta be rotation by an angle of theta. Show that the dot product of the rotated vectors is equal to the dot product of the vectors, the original vectors. Right, let's do that one first, and then we'll look at part B. Okay, so if we look at the dot product of R theta, if we look at the dot product of R theta V and R theta W, using the formula that we derived in, what problem was that, whichever one it was, number 1 or number 2 or whatever, I forget which number problem it was now. But we use the formulas for the rotated vectors, and then just multiply everything out and simplify things. And when you do that, it's just algebra, and you have to know the trig identities here. Cosine squared plus sine squared is 1, sine squared plus cosine squared is 1, and notice these two cancel out when you add everything together, so you get V1 W1 plus V2 W2. Just so it's clear what I'm doing here. Oops. I'm adding that to that. Right. So in other words, what I'm saying is cosine squared plus sine squared is 1, so you're left with V1 W1 here. And then when you add these together, again, sine squared plus cos squared is 1, so you're just left with V2 W2. And notice that these cancel each other. Right. Wasn't sure if that was clear what I was doing, the way that I wrote it down. So, okay. Oh, and then there's another part B. All right, let E equal 1, 0, and be the vector of length 1 pointing along the first axis, and let W equal the vector with coordinates cosine theta sine theta. This is a vector of length 1 that makes an angle of theta with the first axis. Calculate that E dot W is cosine theta, and conclude that in general V dot W is norm V norm W times cosine theta, where theta is the angle between V and W. All right, so let's take a look at that one. Okay, the first one is straightforward. You just use the definition of the dot product. E dot W is 1 times cosine theta plus 0 times sine theta, which obviously is just cosine theta. All right, and then to derive the general formula here, just so I can have something to name, let alpha be the angle between W and the first axis, meaning the horizontal axis, and let norm W be the length of W. Then W has these coordinates, so it's length W times cosine alpha sine alpha, and V has coordinates length V times cosine alpha plus theta sine alpha plus theta. And if you look at V dot W, that's equal to the dot product of the rotated vectors through an angle of negative theta. We proved that already in a previous step. And if you apply the rotations to the vectors here, the rotated vector for V becomes length V times cosine theta sine theta, and the rotated vector W becomes length W times E, and then just use, what we just proved about E times the dot product of E with another vector, and you get the formula. And that's it. All right, question number 4. Given two vectors v and w, we'd expect to have a simple formula involving the coordinates v1, v2, w1, w2 for the area of the parallelogram that they span. The figure indicates a strategy for finding such a formula. Since the triangle with vertices WAV plus W is congruent to the triangle OBV, we can reduce the problem to an easier one where one side of the parallelogram lies along the horizontal axis. So here's the picture that he has in the book. All right, so you have, let me highlight because it might be hard to see what's what here. Let me highlight the vectors in red. This is W, and this is V, okay? So part A says the line L passing through V and is parallel to W, so that line, maybe I'll do that in a color. I probably should have color-coded this before. I didn't think about it at the time, so let me do that here. So this is the line L, whoops. So this one here is line L. All right, the line L passes through V and is parallel to W, so has slope W2 over W1. Conclude that the point B has coordinate V1 W2 minus W1 V2 over W2, and that the parallelogram therefore has area equal to that W1 times W2 minus W1 W2 V2, which is called the determinant of V and W. He does say something about this in the book. There's a paragraph that he has right after this problem. So, but let me go through the solution first, and then I'll read what he has to say there, and then we address what he says in that paragraph in the next exercise. So, so what I did to prove this problem is just find the equation of the line L. And if you look at the picture, this is the equation of line L. Y is W2 over W1 times X minus V1 plus V2. And then set Y equal to 0 to figure out what this point is over here. So point B. So over here, we want to figure out what that point is. So set Y equal to 0 for the equation of the green line, and that'll give us the coordinate. All right, when you solve for X in that case, which is the place where the line intersects the X-axis, that's what you get. So the formula that they asked us to find is what you end up with. So this one here. Okay, and then to find the area of the parallelogram, that's equal to the base times the height, which is given by the X coordinate times W2, which, let me just scroll back up to the picture. Let me erase some of this stuff because the picture's already getting too cluttered. Let me do this in red here. Right, so obviously the area of this parallelogram is equal to the area of this parallelogram here, and the area of the green parallelogram is its base times its height. The base is this X coordinate that we just found, and the height is W2. So you just multiply those two things together, and you get the determinant formula. Okay. So that's the answer for that question. Before I go to problem number 5, let me just read what he says after that problem, just because there's some problems with this derivation, and that's because we made a lot of assumptions in the picture. So let me just read out what he says here. This formula, which defines the determinant, certainly seems to be simple enough, but it can't really be true that the determinant of VW always gives the area. After all, we clearly have the determinant WV equals negative the determinant of VW. So sometimes the determinant will be negative. Indeed, it's easy to see that our derivation made all sorts of assumptions that W2 is positive, that B had a positive coordinate, etc. Nevertheless, it seems likely that the determinant VW is plus or minus the area. The next problem gives an independent proof. So that's what we're going to do in question number 5 next. So let's bring that up. All right, so here there's a couple parts to question number 5. Part A says, if V points along the positive horizontal axis, show that determinant VW is the area of the parallelogram spanned by V, and W for W above the horizontal axis, meaning W2 is greater than 0, and the negative of the area for W below this axis. So let's take care of that part first. All right, so here are the pictures. If W1 is if W1 is positive, then the picture looks like the picture I have in part A. And if W2 is negative, then the picture looks like I have in part B over here. All right, so start with, I do this one in cases. So let V be along the horizontal axis, meaning it looks like the length of V times E, which is the vector 1, 0. All right, so if, case 1, assume W2 is positive. Then if you look at the determinant, you get just using the formula, right? V1 W2 minus V2 W1. That gives you, so V1 is the length of the vector V. And this should not be V1 here. This should be, hang on, let me just fix a typo. This should just be length, oops. This should just be length of V, not V1. Okay, so that V1 is equal to the length of V times 1 times W2, which is just W2, and V2 is 0, so you get 0 times W1, which is 0. So you just end up with the length of V times W2, which is positive because both of those numbers are positive. And the area is base times height, which is the same quantity, so that gives you positive area. The determinant there gives you the positive area. And case 2, assume that W2 is negative this time. So similar argument, the area is length of V times the negative of W2, because W2 is negative in this case, right? So that gives you negative W2 gives you a positive number. So that gives you the actual area, which is, if you look, the negative of what you get if you take the determinant. So the determinant of VW in this case is the negative of the area, all right? So that's part A. Part B, if r theta is rotation by an angle theta, show that the determinant of the rotated vectors V and W is equal to the determinant of the original vectors V and W. Conclude that the determinant VW is the area of the parallelogram spanned by V and W when the rotation from V to W is counterclockwise, and the negative of the area when it's clockwise. So let's do part B next. All right, so first we'll show that the determinant of the rotated vectors is the same as the determinant of the vectors. Here I'm just using the definition of the determinant and also whoops, I didn't mean to do that. And also the formula that we derived for the rotated vectors, right? So the determinant says take the first coordinate of V times the second coordinate of W minus the second coordinate of V times the first coordinate of W. So that's what I'm doing here. And then I'm just simplifying and using some trig identities. When you simplify everything, you get V1 W2 minus V2 W2, which is the determinant of W. Okay. So that shows that rotating doesn't affect the value of the determinant. All right, next we assume that the rotation from V to W is counterclockwise, meaning that W is above, I don't know, it's in the positive direction of rotation, right, from V. So that's what we mean by counterclockwise. Remember, for angles, the convention is that we consider that the positive angle, right? So let theta be the angle from the horizontal axis to V. If you rotate through negative theta, then the coordinates of V are length V times 1, 0, and the rotated vector W through an angle of negative theta has coordinates w1 prime, w2 prime, and here w2 will be positive because of the orientation of the two vectors, right? Therefore, the determinant of VW is equal to the determinant of the rotated vectors, which we just proved, which is equal to the length of V times W2 prime, which we assumed was which is positive because of the way that we rotated, and that's greater than 0. So that's the positive area of the parallelogram. And next, if the rotation from V to W is clockwise, meaning if you start at V, you have to rotate clockwise to get to W, then if we rotate again through negative theta, the rotated vector W has coordinates W1 prime, W2 prime, where W2 prime is negative. So look at the determinant of VW. Again, that's the same as the determinant of the rotated vectors we proved that already, which is equal to the length of V times W2 prime, which is negative, and that proves the problem. And, because, rotation through any angle, this is like completely general, right? The rotation, the determinant is not affected by the angle that you rotate through. So, oh, I need the next page here. Right, question number 6. Show that the determinant is linear in each slot. So determinant V comma W plus Z equals determinant VW plus determinant VZ. Also, they want us to show determinant V plus W comma Z is equal determinant VZ plus determinant WZ, and that a scalar A times determinant VW is the same as determinant A dot V, A times V comma W, and that's the same thing as determinant V times AW. Okay, so it's linear in each of the input slots. And to do this, you just use the coordinates. So it's very straightforward. It's just using properties of real numbers and so on. So if you look at determinant VW plus determinant VZ, using the definition of the determinants, you get V1W2 minus V2W1 plus V1Z2 minus V2Z1. And then just rearranging things and using, the rules for operating on real numbers. You can use the distributive law to factor out the common factor V1 from two of the terms and V2 from the negative V2 from the other two terms, and that gives you the formula for the determinant V plus W plus Z. So those two things are equal. So exactly the same process for the other formula, so I won't go through that in detail here. You can see that it works exactly the same, and same thing for the other one. You can see that when you use the formulas again and the properties of real numbers, this thing here is equal to the other two formulas as well. This is equal to that, and also this is equal to that. So it's basically just, once you have the definition, you just use algebra. Right, and then this is the last problem in the appendix. Using the method of problem 3, show that determinant VW is length V times length W times sine theta, which is also obvious from the geometric interpretation, which is, he says, see the figure, which I have redrawn down here. So if you look at this parallelogram, obviously the area is base times height. The base in this case is the length of the vector V, right? That's this length here. And the height is this length here. The height H is given, by trigonometry. This is the opposite side to the angle theta, right? So that means sine theta is length W over H, or in other words, whoops, I wrote that upside down, sorry. Opposite over hypotenuse, H over length W. And that means that H has to be W sine theta. So the height here is length W times sine theta. So that's just from the picture. You could see that from the geometry, right? But he wants us to prove that using the method of problem 3. So let's finish that up. Okay, so again, we know that the determinant is not affected by rotation, so we can do it in a simple case. So just choose convenient vectors. So let's let V lie along the horizontal axis. So then that means that V has coordinates length v times 1, 0, which we're calling E, and W has coordinates length W times cosine theta sine theta. Then if you take the determinant of V and W using the formula, that's V1 W2 minus V2 W1, which is equal to length V times length W times sine theta minus 0 times length W cosine theta. And when you simplify that, notice you get length V times length W times sine theta, and that's it, right? And then finally, since the determinant's not affected by rotation, this is true in general, right? So, and that's it. Those are all the problems basically for the appendix. Let me just stop my screen share. We still have appendix 2 and appendix 3 to get through. I'm hoping to get through that. Well, I'm hoping to get through at least one of the appendices, one other of the appendices over the weekend. But the appendix 3 is kind of long, so I don't know if I'll have time to finish that one this weekend, but I'm going to do my best. And then hopefully I'll be able to get started on, I wanted to start on chapter 2 in Taylor, because the material in there is related to the material that we just finished up in Simmons. So look out for those videos. Again, guys, thank you for watching. Please like and subscribe if you enjoy this type of content, so YouTube knows to share the videos with other like-minded people. And let me know what you think in the comments. And I'll see you guys in the next one. Until then, keep learning.